So this video covers outputs and actuators. So we'll look at some terminology, then we're going to discuss digital outputs, analog outputs, pulse width modulation, and look at some actuators. So the first thing we need to consider is what power is when we talk about an electrical circuit. So we have something called voltage. Voltage is like the pressure or the force that causes electrons to move. Current is the actual movement of those electrons. So if you take those two and multiply them together, the voltage times the current, that gives us what we call instantaneous power. And if we multiply that power times time, we actually get the energy or the amount of work that can be done. So if you think about a dam, like the Hoover Dam here, you have the pressure is equivalent to the voltage. The height of the water is pushing against the dam, and so that is the pressure pushing it through. And so if they open up one of the gates and allow water to flow through, it's going to be forced out, and so the actual flow of the water is the current. So there's also a term we use a lot called torque. Okay, so torque is a measurement of how much rotational force is being applied. So we have power, which is that instantaneous amount of energy, and in electrical terms, power is measured in watts. In mechanical terms, we measure it in horsepower. So you can actually, there's an equation, you can just simply convert 1 horsepower is equal to 746 watts, or 746 watts is equivalent to 1 horsepower. But torque then is where we take that force and apply it with a wrench or whatever, and we apply a turning force on it. Okay. So here's just another analogy here to kind of consider. If you consider the energy of the Hoover Dam here, and torque is the force of the water pushing on the dam, and so there's more pressure pushing, at the bottom of the dam. And then the power is the energy that is released every second. So if you're releasing that energy, okay, so the torque is like the pressure or the force that is there, but it's not moving. So power needs to actually be moving. So here we have a potentiometer. A potentiometer is a resistor. What it does is it opposes the flow of current. And the big thing about a potentiometer is that we can adjust the amount of resistance for this center terminal. So we have 3 terminals. We have 2 outer terminals and then the center terminal. And there's a wiper connected to the center terminal, and so as you turn the knob, you adjust that wiper and it adjusts the resistance. Alright, so when we have a controller and we want to send an output out, we can send output out to digital out, which digital we've already discussed is a 1 or a high and a 0 or a low. And so when we're talking about sending a digital out, we're talking about we can either send out a 1 or a 0, or we can send out an analog out. And And so an analog out goes through what's called a digital to analog converter. So you actually take a value and convert that into a voltage, but that voltage range will change depending on the amount of output that you put on it. And then we also have something called pulse width modulation. Pulse width modulation is basically digital out, where you send out either a 1 or a 0, but you send it out in pulses, and the width of those pulses change. And so by doing this, we can send out instructions, or we can send out kind of like a pseudo analog output. So if we're going to connect an output to our controller, we need to make sure that we don't draw too much current, because too much current can overload and damage the controller. So if we look at our Beaglebone, a single output pin can handle a maximum of about 4 to 6 milliamps. So if we wanted to hook up just like an ordinary LED, a normal LED can use about 1.5 to 2.5 volts depending on the color of the LED. So like red and green bulbs use about 1.5 to 1.8 volts, but a blue or a white LED actually needs a higher voltage, so it uses 2.5 volts. But the problem is that like our Beaglebone controller, it actually works at 3.3 volts. So if we send out a digital out, that digital out, if it's a high, is 3.3 volts. And so if you try to put that 3.3 volts through a LED that is going to just require 1.5 to 2.5 volts, then it's kind of like opening the floodgates on the Hoover Dam there. You're going to allow too much water out, or too much electricity in this case, and cause damage. So what you have to do is anytime you connect up an LED, you need to wire in an extra resistor here so that the LED can handle its 1.5 to 2.5 volts depending on what it wants for its color. And then the resistor will basically absorb the rest of that voltage and keep the current within check. Now, if you wanted to drive something larger, like a relay or a motor or something like that, you have to be careful because, again, they're going to want way too much current and the controller can't output that much. And so here's a simple circuit that uses a transistor as a digital switch to activate a relay. And the relay has a coil here, so the relay is going to need a significant amount of current. So what we do is we drive this transistor by putting a 1 or a high out, so we have like 3.3 volts here. Now this transistor between what B and E, the B stands for base and E is the emitter, and it wants 0.7 volts. And so what happens here is this 1K will basically, again, where our Beaglebone is going to output 3.3 volts. And so we can only have, this transistor only wants about 0.7 volts here. And so we need this resistor to take up the rest of that voltage, the difference between the 3.3 and the 0.7 volts. And so this little circuit here will allow that, and it'll turn on this transistor, and then this transistor then can feed a lot of current through the relay to activate the relay. Now relays or electric motors, they have this coil in it. A coil is another word for coil is an inductor. What this does is it stores magnetic energy in a magnetic field, and when you shut that off, that energy needs to be discharged. So when you try to shut off the transistor, you need to discharge the energy out of this coil. And so this diode here is what we call a freewheeling diode. And so what happens is when the transistor shuts off, this coil will start dumping its energy, and it'll go through the diode and come back through, and we have a little loop. Whoops. We have a little loop here, and it'll just like dissipate. There's also resistance in this coil, so the energy will dissipate, but it gives it a chance, a place to dissipate that energy by just looping around here, and it protects your transistor. Without this diode, you could very easily destroy the transistor. Now, a solenoid is an actuator that basically just moves a bar or a metal shaft. And so the idea is when you energize, it's a coil, and when you energize that coil, it draws in the metal bar. And then when you break the circuit of the coil and it de-energizes, there's a spring over here which will push the bar back out. Okay. This is an electric relay here, and what it does is, you can see it's kind of says here 5 volts. And so what this will do is you can activate this with our 3.3 volts up to 5 volts from our Beaglebone, and we can activate this relay. And then on the other terminals, then you can actually power something very large. So you see this says 250 volts AC at 10 amps. Okay, so we can activate this relay with our Beaglebone, with our 3.3 volts from our Beaglebone. It says 5 volts, but 3.3 is enough to activate it. And that'll activate this relay, and then you can literally power like a light or even like a small heater or something along that lines with this relay. So the way the relay works is it allows you to activate it with a low voltage, and then you can drive a much higher load with much more current and much more voltage in here. So this is a wiring diagram of it. So here we have like our voltage, which would be our pin coming out from our Beaglebone of 3.3 volts. So we would turn this on and make this high. That would energize this coil. This coil then causes these contacts here to close, and that allows this higher voltage to actually drive current over to a larger load. So relays are electromechanical switches that allow us to drive very large loads and control them with a small controller. Here's a picture of a digital to analog converter. So again, we want to go from digital to analog output. And a simple circuit that will do that is a circuit like shown here. This is a op amp, and this op amp down here, this triangle represents this op amp, and we connect it here with these switches. And if you notice here, you notice that these are numbered 1, 2, 4, and 8. So if you go back when we talked about binary, remember you had like your 1's column, your 2's column, your 4's column, and your 8's column. And so basically that's the way this is set up, only it's actually like 8 divided by 8 here. This 8 divided by this 8. So this is actually the 1's column down here, because you have 8 divided by 8. And then your 2's column is the next one. You have 8 divided by 4, so that's 2. And then here you have 8 divided by 2, which is your 1's column. And so here's the mathematical equation for this. So when you close these switches, you can close one of them or all 4 of them or any combination of them. and this gives you a 4-bit digital to analog converter. And so it allows you to output a range of 16 different values from 0 up to 15 different volts here. All right, so here's an example of trying to generate a sine wave using that 4-bit digital to analog converter. Now, when you do this, the problem is that your controller is running through the program, and when it changes from a 0000 to 0001, and it steps up these bits, and so, but it only does that every so many seconds depending on the clock cycle of your computer and how long it takes to execute the code. And so therefore you don't get a perfect sine wave, but you get this kind of step waveform coming out. So it'll hold when you put out 0001, it'll hold that value until you put out a different value. All right, so our next type of actuator is an electric motor. Okay, so electric motor is a device that takes electrical energy and converts it into mechanical or rotational energy. All right, and sometimes we use the term servo motor. Servo motor just implies that it actually has some sort of built-in control, so you can send it data and you can control the speed and or position based on the type of data that you send it. So the first type of motor that we can talk about is a DC brushed motor. So a brushed motor here, it has these electrical brushes, which are basically like a carbon material, and there's a coil inside on what we call the armature, which is the part that rotates. And so these are applying current through the DC motor. Now, the advantage of a DC motor like this is it actually has very high starting torque. So it's actually very powerful, especially at low speeds. So it's good for getting things started. However, the downside is that these brushes will wear out. And so you have to do maintenance on it occasionally to replace the brushes. Alright, so some of the nice things about brushed DC motors is, number one, they've been around for a very long time, so it's very mature technology. They're relatively low cost, and they can have a very like I say, a lot of torque at low speeds, okay, and a fairly linear torque to speed relationship. And they can actually go to up to very high speeds and very quickly. Okay. The downsides, as I mentioned, is that they do wear, and also those brushes, there's sparks that occur at those contacts of those brushes, and so if you're in an environment where you have like maybe like explosive gas in the air, those sparks could cause an explosion. So you can't use them in those types of things. Now, a newer technology is what we call the brushless DC motor. And the way this works is that the rotating part actually has permanent magnets. And so therefore these do not actually have to rotate. So all we do is we have to activate coils on the stator, on the part that doesn't rotate. And so we have coils there, and we have to pulse those, and we can get the DC motor to rotate. All right, but there's two downsides to the brushless motor. Number one is you have to have a controller to control it. Okay, so with the DC motor, all you need is DC. With a DC brushed motor, all you need is a DC voltage and the thing will run. But a brushless DC, you need more than just the DC voltage to make it run. You actually have to have a controller because you have to make these coils go on and off so that you can activate it and get it to move. Okay, so, and you also have to have sensors on here. These are called Hall sensors, which are basically magnetic sensors that you can use to detect where it's at so that the controller knows when to activate. The other thing is that the speed characteristic is not as constant as with a DC. So you have a continuous torque area, but that continuous torque area, your torque is much smaller than a brushed DC motor. Okay, so they require a controller to work, and so therefore they're going to be more expensive than the brushed motor. But a lot of times they're more efficient. They don't require as much maintenance. I mean, sometimes a bearing might go out on them, but you don't have to worry about the brushes wearing out on you. Alright, and another type of motor we have is a stepper motor. So a stepper motor is kind of like a brushless DC motor, but it's designed to move in just steps instead of at constant moving. So you have to keep giving it steps to keep it moving. So here's kind of an example here. Again, we have like a permanent magnet on the rotor part that's going to rotate, and then we have these coils, and the idea is we can control the speed and direction by putting pulses on these various different coils, and we can get this thing to rotate. So there's a really nice video here that I have a link to here. You might want to watch this. It really does a nice job of explaining how this stepper motor works. So some advantages of stepper motors is that you can do precise positioning, and you can control the torque, and you can hold the torque when it's not moving. So it's good for intermittent moves and can hold that place for a very long time, and lower cost than a servo motor with a more advanced controller. But it's not ideal for non-stop usage, so they're not really designed to just go, 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 go. They're designed to step and then hold and then step and hold. So you can make like multiple steps, but then they're kind of intended to stop for a little while and let them cool off. All right. So then we have AC induction motors. Okay, so AC induction motors, and then this is called a servo motor. So again, it has to have a controller. But the way these work is the controller is what we call a variable frequency drive. So what you can do is you can change the speed of the motor by changing the frequency. So that's why they call this variable frequency controller. The nice thing about AC induction motors is that they do not have brushes. They have a lot of torque, but they don't have brushes. They can run at a constant speed as long as you're maintaining this frequency constant. All right, but the speed will decrease when you load it, so that when you get more load, you get something called slip, and it gets out of sync and will maybe run a little bit slower. All right. So we also have what we call analog servo motors, and these usually are fairly small devices, but the way these work is that they have built inside of them a little printed circuit board with a controller chip on them to control them. And then they usually also have a lot of gearing on them, and then just a standard DC motor. And the way these work is you send a pulse width modulated input to the controller, and then it controls the direction of the motor and the speed of the motor. All right. Now, when you're talking about motor specs, there's two big things that we talk about. And one of them is the speed. How fast is the thing moving? And number two, how much torque can it hold? And so torque is a measurement of distance times the force. And so like here, if we have this connector here, we connect to a servo, we could put say 5 pounds here. I mean, it'd have to be a pretty big servo for that, but say we have like 5 pounds and we're 1 foot away. But if we, or however, whatever this distance is, 1 unit away, but say it's foot, so this would be 1 foot times 5 pounds, so that would be 5 foot-pounds. On the other hand, if we go twice the distance, then we only have to have half the weight. I know that it looks actually maybe a little bit bigger here because I put in 2.5 there, but it's actually only half the weight, 2.5 pounds, because it's twice the distance, but it gives us the same torque. All right, so for our analog servo motors here, again, we send what we call pulse width modulated signal. And so they're designed that you're sending this, what we call a square wave, or sometimes a rectangular wave because it's not perfectly square. And so what you have is you have this pulse. Usually this pulse is running at like 50 hertz, which means you have a pulse every you have 50 pulses every second is what 50 hertz means, or every 20 milliseconds you have a pulse. But then you adjust the width of that pulse. And depending on the type of servo motor, you can either control the speed of it by adjusting what they call the duty cycle, or the width of this pulse, or you can just adjust the angle of the servo motor. All right, so when you look at the GPIO pins, remember GPIO stands for General Purpose I/O pins. And if you look at the ones that say PWM, okay, these are the pins that can support pulse width modulation output. And so there's quite a few of them that kind of have this like darker orange color here. But there's I don't know, 6 or 8 of these that you can use to generate a pulse width modulated signal. So you need to make sure that you're not using one of these pins for something else, and then you can send that pulse width modulated form to it. Okay. All right, now to run the Beaglebone, and if you're trying to run like a servo motor or a stepper motor, you have to be careful because they're going to want a lot of current. And so there's 2 different connectors. There's the standard USB port, which is enough to power the Beaglebone itself. But if you want to then power a DC servo motor or something, you need to actually connect it to that other connector, that DC direct current jack in there, and apply 5 volts there through a separate power supply. Because if you're just connecting it through the USB port, it won't have enough to drive a motor. And if you're trying to drive a big motor, you just need to connect it separately with the circuit shown before. Okay. So with the DC jack, you're allowed to go up to 1 ampere of current. But if you're just doing the USB, it can only handle about 1/4 of that. Okay, so You have to be very careful when you're trying to power big loads. And again, you really, you can't power anything more than 1 ampere on this. All right, if you're just running a standard GPIO pin for digital in, digital out, okay, then your current, again, should be no more than 8 milliamps maximum. Okay, so to be safe, you really want to keep that current closer to, say, 4 milliamps. And so the way you can determine that is we know that these pins are going to be high at 3.3 volts. And so you need a resistance of, say, about 825 ohms on the output to keep it below 4 milliamps. Now, if you have an LED, remember LEDs are going to take some of that voltage depending on the color of the LED. And so, you would have to determine which color of LED that you're going to use. But just in general, for this 3.3 volt pin, if you put a 330 ohm resistor in series, it's going to keep you around that 4 milliamp for those pins. Anything more than that, and you want to go back and look at that transistor circuit that I showed earlier to drive larger loads. Now, when you're trying to activate something, say like just an LED with a Beaglebone, you can do what's called an active high, where you want a high or a 1 out to activate the LED. So the way you would do is you connect that. In this case, I used a 470 ohm and then a blue LED. Now, I said on the other slide 330. If you use a 470, it'll still work, but the bulb will be much dimmer, and the current will be quite a bit less. Okay. Now, on the other hand, if you just wire 3.3 volts to the high side of your resistor here, and then you put your pin, then you put your pin down here, so when the pin goes low, then the LED will come on. So if the pin is high, you have 3.3 here, 3.3 here. They're the same, so there's no current flow. Right? To have current flow, you have to have a difference of voltage. So if I just wired this to 3.3, and then the pin was high, then that would be what we call an active low. So when the pin was high, you would have no light, and then when the pin went low, then the light would come on. Okay. Here's a picture of driving the transistor. In this case, I have the 2.2 kilo ohm resistor, so it's a slightly larger resistor than I had before. And then I put in 3.3 volts here, and that will activate this. So this is kind of trying to show you it's like a switch. So the switch is closed, and current is going to flow through here. And so the output is actually, when you put in a 1 here, your output over here is a 0. So this output is 0, but you will have current flowing through this 100 ohm resistor or whatever this resistor is. Okay. On the other hand, if you put out a 0, then that opens this, and so this output here would be a high. So this is what we call an inverting circuit here. So if you're looking at driving this output as a high or a low to something beyond this, then it's inverting. So when you have a high coming in, you get a low out, and then you have a low, you have a high out. All right, So here's an example again where we're driving this relay. So I have a relay here, and this arrow is just showing the measurement of the currents, and this is what we call the base current. And so we have, like, when this goes to a 1, we have 3.3 volts here, and that turns on this transistor, which allows current to flow through the coil of this relay, which then activates it. So we have two different connections here. We have what we call a normally open connection and a normally closed connection. And so when we put a high out, we turn on this transistor, and that applies power to the normally open connection, and it would go to the load. Alright, so when we're trying to set this up in node red, okay, we have to be careful here when we select the type of output. So if we select digital, that means we're going to have a high or a low out. So where it says 1 here, that's actually going to be 3.3 volts. If we choose analog, okay, the analog, we can put out a value between 0 and 255. Okay. And so that's actually a pulse width modulated signal. And so it's actually going to be 0 or 3.3 volts, but it's going to be turning on and off based on the value that you put in. So if you, it's an 8-bit range that you can put out. So if you put out 255, then that means you're just putting it on high. So that would almost just be like digital on all the time. But you can cut that in half. If you output 128, it'll be on half the time, off half the time. And then if you choose the servo again is a pulse width modulated, but it's going to be out there, and we can put in values between 0 and 180 degrees. Alright, so that's it for our outputs and actuators.